Hi, I've wanted to do a video on guitar cables for quite a while, and finally getting around to doing it. There's a lot of false information on the net, no kidding, about how guitar cables affect your sound and what are the parameters that you want in a cable, such as wire gauge, type of metal, like copper or silver or anything like that. Well, we're going to look at all that stuff and dispel the myths. Okay, we're going to look at the mathematical model first. This is college algebra. If you don't understand that, you won't understand the math, but at least you can follow the conversation, I guess. It's really not that complicated. Okay, we'll start with the pickup. The representation is an AC current generator. How that works is the strings are metal and they're magnetic, and they attract the field from the magnet in the pickup through a property called reluctance. And when you pluck a string, it actually vibrates the field because the field's kind of stuck on the string. And that field vibrating through the coil in the pickup causes an electric current. Same way hydro generators work. So we represent that with the inductance and the resistance inside the pickup. It's a bit of capacitance, but it's really too small to notice, unless of course you turn your tone control off. That's a capacitor outside the pickup. We're not going to look at that. Since it's a low Q circuit, they always put the coil in series with the resistor, even though it's one part. From an engineering standpoint, it's two parts. You got the 5K ohm resistor and typical single coil pickup for like a telly or something would be 2.5 henries. That's quite a bit of inductance. You might have like 8,000 turns of wire inside that thing. Next we have the cable. We'll look at that in a bit. The amplifier, it's a 1 meg ohm load usually. I'm talking about a vacuum tube amp. This is the point we're interested in. That's the voltage that we're going to amplify to listen to. It typically goes into the grid of a tube, but there's no grid current. So since there's no grid current, there's no voltage, there's no nothing. It more or less doesn't exist. It just takes the electrostatic field, you might say, modulates the electron beam and blah blah blah. Anyway, now the current is going to go through here, down here, and back. There's one other place it's going to go, and that is capacitance of the cable. Now, that capacitance is quite a bit, especially when you have a 1 meg ohm load. The resistance of the wire, might surprise you to know, is negligible. It's meaningless. It has no effect in this circuit. Why? Because that's a 1 meg ohm load. This is basically a voltage divider. Current in here causes a voltage. Across this impedance, we'll call Z1. The current continues, now takes two paths. Because it's AC, it goes through the capacitor. And of course goes through the resistor here. So that is Z2. So the voltage divides. There's a voltage inside here. It is equal to this voltage across this impedance plus this voltage across this impedance. So this is a division. That divides the voltage. 1 meg ohm load and whatever this turns out to be in capacitive reactance. Now you're probably used to speakers or something where you have a 4 ohm load, so you want heavy gauge wire. Or maybe in your house you want heavy gauge wire to power your stove or something at several thousand watts. That's 1,000,000 ohms. if you wanted to divide that voltage in half, you'd need 1,000,000 ohms here. So unless you have 1,000,000 ohms in your guitar cable, it doesn't really matter. 0.01 ohm, 0.2 ohms, 0.1, 1, means nothing. You're not going to get a division there. And as far as inductance, some people have noticed or mentioned or whatever that you could coil up your guitar cable and maybe get some inductance. Doesn't matter. You get 2.5 henries here in the circuit. 2.5 henries. You coil up your guitar cable, you might get a couple of micro henries. You know, if you have a bright flashlight, really bright, take it out in noonday sun, you won't even see it because the sun is so bright. It's the same thing here. 0.1 ohm, you're not going to see it with a 1 mega ohm load. You get a couple of micro henries of inductance in your cable, you're going to see it with 2.5 henries over here. It's not how the world works, boy. Okay, so talking about the division, the formula to calculate it would be Z2 over Z1 plus Z2, right? So whatever is here, you'd have like Z2, say that was 1 and that was 1, you'd have 1 and 1, so 1 over 2 is a half. Equal resistances, it would be a half, right? So that's the formula. To get it into dB, we would need 20 times log, so dB loss equals 20 times log of this. That's just to get it into dBs because we're dealing with audio. Okay, next. We wanted to see the voltage here, so we need to calculate what's the division at all the frequencies of interest. Now guitars, 6-string guitars, start off, the E string is about 82 Hertz. So we'll start at 100 Hertz. We'll make a graph with a spreadsheet in the computer. Of course I'm not going to do it all. It would take forever. So 100 Hertz. This coil has a certain inductive reactance at 100 Hertz. The formula for that would be 2 pi frequency, which is 100 times inductance. Now I didn't want to waste time with the calculator, so I've pre-done everything, and that would be 1570 ohms. Now the capacitor, I measured my 6-foot cable here and I got about 500 picofarads. That's millionth farads. Or 500, so say 0.5, 10 to the 9th, so that's 500, 10 to the 12th. Yeah. So the formula, I'm going to put in here XL, right? XC, the effective capacitive resistance. It's called capacitive reactance. It forms an impedance. Formula is 1 over 2 pi frequency capacitance. Now at that frequency, with that small capacitor, that's going to be very high. And it's actually 3.2 million, so 3.2 exponent 6 ohms. 3.2 million ohms at 100 Hertz. Now you might think, well, is that going to affect the tone? Well, yeah, when you get up to a couple of thousand Hertz, that goes below 1 million, right? So we no longer have a 1,000,000 ohm load. We might have 500K, 100K, stuff like that. So the high harmonics are going to be shorted out by that capacitor. Now the coil, as the frequency goes up, this number is going to go up, so it's directly related. So when we get up to a few thousand Hertz, or up into the harmonics, this guy's going to kill the treble. Your pickup automatically kills treble because of its inductance. Your cable kills treble because of its capacitance. So most guitar amps have a filter to increase high frequencies. Now a humbucker has maybe 7 henries, maybe more, so that's why humbuckers sound so much darker, bassier, because they kill the high frequencies more. But we'll see that on the graph. What we got to do now is come up with the math. We need to figure out Z1, Z2. And again, I've pre-done stuff here so I don't have to waste time with a calculator. Alright, Z1. We need to add the resistance to the reactance. So that's pretty simple, right? It's 5K plus, well, that's out of phase. With AC you have this thing where things can go out of phase. You know, where you have one waveform like that and the other one's out of phase, like that. One of those is current and one of those is voltage. So we have to account for that. You can't just add these numbers. You can't add that to that. They're out of place. So that becomes what we call plus J. And 1570, that's this number. So plus J 1570 ohms. So 5K ohms plus an out of phase 1570 ohms. How do we handle this out of phase stuff? Well, we use vector arithmetic because they're 90 degrees out of phase. So we can use Pythagoras' theorem, which is the square root of the sum of the squares, right? So that's equal to the square root of 5K squared plus 1570 squared. That turns out to be 5240 ohms. 5240 ohms. So 1570 plus 5K out of phase adds up to 5240. You can see coil doesn't have that much effect at that frequency. It's not really 1570, it's 240 as a magnitude. Now we also have an angle. The angle, of course, is arctan x over r, which is simply the arctan of 1570 over 5K, which turns out to be 17 degrees. So our answer is 5240, 17 degrees. So that's it for Z1. Next, we got to do Z2, which is two parallel branch currents. A little more complicated. Z2. There's a method of doing two parts in parallel, and it's called the times over plus. You simply take the multiplication of the two values and you divide it by the addition of the two values. That would be that value and this value. They're both pretty high numbers. So the times becomes 1 meg times. Now again, that's out of phase, it's a capacitor. The phase is reversed, it's minus 90 degrees. And we indicate that by saying it's minus J, and it's 3.2 E6, right? 3.2 E6. And that's going to be over the addition of them, which is 1 meg, plus minus J, which of course simply becomes minus J, 3.2 E6. Now the top part's fairly simple. When you multiply a real number by an out of phase number, you simply get a bigger out of phase number. So that becomes minus J, 3.2 E6 times 1 E6, so that's 3.2 E12. Oops. Big number, 3.2 E12. Bottom again, it's a complex number, and it's out of phase, has to be added vectorially. Again, Pythagoras comes there to our aid. So it's the square root of 1 million squared plus, now when you multiply a minus number by a minus number, you get a plus number, so that's simply plus 3.2 E6 squared. And we move along to, you can't have a negative resistance, obviously. Well, you can, sort of in theory, but we get rid of that minus J. We change that to a magnitude, 3.2 E12 at an angle of minus 90 because it's purely capacitance. That part of the formula. It's a capacitor multiplied by 1,000,000, so it's a big capacitor. Capacitor is minus 90 degrees. The bottom part, the Pythagoras, ends up being 3.34 E6. 3.34 E6. And its phase again, of course, is the arctan of the reactance over the resistance. And where do I got that? Minus 73. Because it's a capacitor, you'll find in these formulas is you're almost always going to get negative angles. Okay, so we got to continue along. We have to solve that. That's easy. It's 9.54 E5. So it's 0.9 million, right? And the angle turns out to be minus 17, right? 90 minus 73. Alright, so that's our magnitude. Now in this equation we got to add Z1 to Z2. We got to add this to this. I suppose we could add them as is, but normally, because the angles are the same, we could probably do it, but for the other frequencies, the angle's not going to be the same. So what we need to do is convert this to a rectangular notation. So the cosine of the angle times the magnitude is going to give us our in-phase number, which is, like I said, I already did this, 9.1 E5. And the sine of the angle times the reactance is going to give us 2.86. That's a J number. 2.86 E5. Again, 0.2 million, and it's negative. So Z1 is both this number in rectangular and this number in polar. Z2 is this number in polar and this number in rectangular. So Z1 plus Z2. Finally, get somewhere here. We're going to add the rectangulars, so that's 5K plus J 1570. Alright. Boy, what did I do there? Weird. 7 plus Z2. That's this number, right? Plus 9.1 E5 minus J 2.86 E5. So we add the 5K to the 9.1 E5. We add the plus J 1570 to the minus J 2.86 E to the 5. And we end up with 9.15 E to the 5 minus J 2.84 E5, which again we have to use our square root of the sum of the squares. Thank God for computers and spreadsheets. So that's 9.15 E5 squared plus 2.84 E5 squared, blah, 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 equals 9.58 E5 at an angle minus 17 degrees. So now we just have to do the Z2 over Z1 plus Z2, and we can get our dB loss. dB loss equals 20 log 9.54 E5 minus 17 over 9.58 E5 also minus 17, and that comes out to that ends up being equal to 9.996, which is 0.04 dB, which is practically nothing. Hardly measurable and definitely not audible. So that's at 100 Hertz. That's the division, the voltage, the loss, next to nothing. So next step is to make a spreadsheet, put this formula in, plot all the frequencies from 100 up to about 10K or so, and have the computer draw a graph, and then we'll take a look at the graph and we can see what it looks like. We'll be able to change values, be able to change our capacitance in the spreadsheet, be able to change type of pickup, parameters, impedance of the amp, everything, and draw charts for anything we want. Then, at the end of the video, I will feed a swept audio generator through a tele pickup into a scope, and we'll verify everything. We'll also look at some of the myths about whether the resistance in here has any effect, or inductance if you coil up your cord, or any of that. Or we'll check for the truth and not the bullshit that's all over the net. So let's take a look at the spreadsheet. See you in a minute. Well, a minute for me maybe, not a minute for you. Okay, this is without a cable, more or less. I've removed the capacitance. You can see the dip in the high frequencies. I'm going to put in 500 picofarads, simulate a 5 or 6 foot cable. You can see quite a peak right in the mid-range, 4400 Hertz there on the chart. It's over 15 dB peak. It's a resonance caused between the inductance of the pickup and the capacitance. If we decrease the impedance of the amp, you can get rid of that peak. Sometimes using a pedal will help you tame the peakiness from your cables. Also, if you use a longer cable, let's put in twice the capacitance. It could be like 12 foot or more cable, 1000 picofarads, and we decrease the frequency of the peak, as you can see. More capacitance, lower frequencies. It's typical. I'll put that back. Now, humbucker has more inductance, so let's double the inductance. And again, it's a lower frequency. So your cable and your guitar together can really affect your sound. Okay, got my sweep generator and my scope. As you can see, this represents the sweep starting at about 20 Hertz. It's actually probably a little higher, probably around 50. Sweeping up to about 20,000. Probably doesn't go to 20,000, probably goes to 10. I've been playing around with the range, try to get it closer to what we can actually hear. So okay, now if I feed that through tele pickup here, we can see the pickup doesn't like high frequencies and kills them off because of its inductance. The scope, by the way, is 1 meg load because I have the probe set to ×1. So that's your would have been your response if you had a perfect cable. In other words, no capacitance or anything in it. Most guitar amps have a filter to increase high frequencies. Okay, I'm going to add in 470 picofarad. You can see it peak. It's the same peak we noticed on the spreadsheet. That would represent the 6-foot cable. The highs are really cut down. We got a peak up here. Okay, I have a switch in here with some leads and I can add in some stuff. Some people worry about coiling up their guitar cord. Well, they'll never get that much of a coil, but if you had a 100-foot guitar cable and managed to coil it up, let's put the coil in and we can see coil doing anything. Nope, not a thing. Why? Because this pickup's about 2.5 henries. This thing's not even a millihenry. Imagine what your guitar cord would be coiled up. Maybe a microhenry. Okay, let's go on. Let's talk about wire gauge. A lot of people are worried about whether their cable's 0.1 ohm or 0.01 ohm or something. How about we put a resistor in there, simulating a really fine gauge wire, or perhaps wet spaghetti or something, or whatever. Again, see any difference? Nope, nope, nope. Wire gauge don't matter. The metal your cable's made of don't matter. Resistance of your cable don't matter. So what did I add in here? An ohm? A couple of ohms? I don't know if you can see that, but oops, that's 1,000 ohms, boy. That's like a cable going from New York to Baltimore. Well, that's it for debunking all the idiot myths about guitar cables. See you later.